today we are going to talk about a class of parallel concatenated convolutional code called turbo codes. Now, what is concatenation? In concatenation, we take small codes and we combine them to create a more powerful code. Now, this idea of concatenation was proposed by David Forney, and what he did was he took two codes. So, there was one code called outer code, and then he had another code called inner code. And so, this is you are creating a more powerful code using two codes, and you send your coded bits through a channel, and then you have the decoder for inner code. So, you have inner decoder, and then you have a outer decoder. So, this is your or you could also view this as your super channel, this as your super channel, and these are codes on that. Now, this is a very simple idea of combining two relatively simpler code to create a more powerful code, and these codes could be block codes, convolutional codes, we could use any one of them. Now, this is one class of concatenated codes. Now, there are various ways in which you could concatenate code. This is an example where two codes are serially connected. If you see, the output of the first encoder is given as input to the second encoder. Now, there could be a configuration where two encoders are connected in parallel. So, you have two encoders, they are connected in parallel. This is your encoder 1, encoder 2, you could have like this, or you could have a combination of both. So, you have some parallel concatenation, this is a combiner, and then you have another code encoder 3, which is serial. So, this is a combination of parallel concatenation and serial concatenation. This is like hybrid concatenation. So, there is various ways in which you can concatenate two codes. There is a configuration which is called product code. So, you have a let us say k cross k information bits, you add some parity bits here corresponding to each of these k bits, you add some parity bits, and then you can read these information sequence column wise also, and you can add parity bits corresponding to these columns. So, you can have codes like this. This is called incomplete product code, and then you could also have checks on checks. So, that is a product code. So, there are various ways in which you could concatenate or combine two smaller codes to create a more powerful code. In this lecture, we are going to talk about one such class of concatenated codes, which is called turbo codes. It is essentially a class of parallel concatenated codes. Now, if you recall, Shannon in his celebrated noisy channel coding theorem has mentioned that as long as we choose our transmission rate to below channel capacity, we can reliably communicate over a communication link. And his proof was basically based on fact that if you randomly select a code word of very large length, then you can show that probability of error will go to 0 as long as your transmission rate is below channel capacity and you transmit with long code words. Now, people from 1948 onwards were trying to design codes close to channel capacity, and the problem was if you design a very random like code which does not have any decoding structure, then the decoding complexity is very large. However, if you put lot of structure into the code, then it is not really random like and its performance is not very good. So, how do you design a code which has enough randomness into it, but then enough structure also which can be exploited for decoding the code. So, that is basically the challenge, to design a code which has good minimum distance, but then we should be able to decode it also. Now, these turbo codes are a class of codes which are random like, and we will show you how this random look like because of the inherent interleaver structure fitted in this parallel concatenation structure, and there is enough structure in the code which allows us to do efficient decoding of these error correcting codes. So, what does an encoder of a turbo code looks like? It consists of parallel concatenation. So, maybe I will first show you the diagram. It consists of parallel concatenation of two encoders. This is one encoder and this is second encoder. And note, the same information bit is going to two encoders. So, this information bit is coming here, and the same information bit after getting interleaved. Interleave is nothing but reordering of the message bits. It is entering this particular encoder, and this is your systematic code. So, you have your information bits here, and then this encoder is generating this parity bit, this encoder is generating this parity bit. So, if you notice, this encoder consists of convolution encoder as a constituent encoder in a parallel concatenation scheme. So, the key is parallel concatenation. So, the same input is going to both these convolution encoder. Next thing to remember is, we are using systematic convolutional encoders. Why are we using systematic convolution encoder? When we talk about the convergence properties of turbo code, then we will mention basically the systematic encoders have better convergence property under iterative decoding algorithm, and that is why initially proposed turbo codes use systematic convolution encoder. Subsequently, people have also worked on design of non-systematic turbo codes, but the ones which were initially proposed in 1993 by Baru et al. Used systematic convolution encoder. The third thing to note, very crucial, is the use of recursive encoders. What is recursive encoders? These are feedback encoders. So, there is a feedback from the output to the input. Note here, there is a feedback from the output going to the input, there is a feedback from the output going to the input. So, these are all feedback encoders. Now, why do we need feedback encoders? I will just give a very simple example to illustrate. So, we know that we would like to have a large minimum distance of these codes, because larger the minimum distance, better is the error correcting capability of the code. So, let us just consider a very simple case. Let us just consider that you have a memory 1 code. So, let us just say memory 1 code could be G of D. So, this could be, let us say 1 plus D, 1 plus D. Now, usually the input bits, and this is systematic, right. So, this comes here. So, usually the information sequence that have low weight can create low output weight sequence also. So, let us look at weight 1 sequence, let us say 1 and all zeros. So, that is just 1. Now, if this input comes in here to this particular encoder, note this will produce an infinite length of 1, and same this 1 when it comes here after interleaving, this will also create a large number of 1s. Whereas, if instead of recursive encoder, if we would have used a non-recursive encoder, let us say if we had used a feed forward encoder 1 plus d, then what would have happened? This would have been just 1 plus d, and of course, this would have been also 1 plus d some shifted version of that. So, you can see that we can get better distance by using feedback convolutional encoder. So, that is why this is very important that, and this was a key innovation for this code, that when they used two parallel concatenated codes, the convolutional encoder which was used was recursive convolution code. It was systematic because systematic codes had better convergence property. So, remember these two things. So, what are the components of the turbo code? So, first thing I said, it is a concatenation of two or more encoders in a parallel fashion, as opposed to serial concatenation. In serial concatenation, what happens is, so there are bits coming in here, this output for first encoder, that is fed as input to the second encoder. So, this is your encoder 1, encoder 2. So, the output of encoder 1 is fed as input to the second encoder, but in parallel concatenation you are sending the same information parallelly to both the encoders. Now, what is the role of interleaver and what is interleaver? As I said, interleaver just permutes the bit. So, it just reorders the bits. So, some bits which were there in, let us say, bit location 1, maybe it will put in bit location 56, and it just shuffles bits here. Now, the design of interleaver and the role of interleaver is very, very crucial for turbo codes. So, let us illustrate that again with a simple example. So, what we are considering is this recursive or a feedback encoders, and we are considering a very simple feedback encoders, which is memory 1 two-state convolution encoder. Now, as I said, input 1 sequence cannot terminate this encoder. If my u of d is 1 and g of d is 1 by 1 plus d, then what is my v of d? It is u times g, which is 1 plus d, and this is 1 plus d square. So, this I am getting a string of 1s. The same thing, when you permute, it does not change the weight distribution, it just reorders the bit. So, again the weight 1 sequence that you will get here cannot terminate this encoder. So, I will get a large output weight. Now, let us look at weight 2 sequences. Let us say if I have 1 1 and all zeros. So, let us say 1 1 and all 0, that is 1 plus d. So, if my input is 1 plus d, then what happens to the output of the first decoder? Now, this sequence can terminate this encoder, and what I will get here is, I will just get a 1. I will just get a 1 because my ud is 1 plus d and gd is 1 by 1 plus d. So, what I will get here is 1. So, I am getting parity weight out of this parity check bit. I am just getting 1 and all zeros here. Now, to have a code with overall weight large, remember my input is only 2 weight, my input is 1 1 and all zeros. So, here also I will get 1 1 and all zeros. So, here I am getting only weight 2, here I am getting only weight 1. Now, to have an overall weight large, what would you like? You would like to have a large number of 1s coming out from this parity check bit. Now, how can you do that? Now, remember what is interleaver? Interleaver is just a permuter, it is just shuffling bits. So, if you had bits which are like this, let us say 1 1 and all zeros, and typically the block sizes are very large, I mean 1000, 10,000, let us say 10,000 or something like that. And let us say your interleaver, what it did was, it kept this 1 here, but moved this 1 to the last location, and in between you had all zeros. So, this was your 1 plus d, and this becomes 1 plus d raised to power, let us say n minus 1, because the way you design this interleaver, it rearranged the bits in such a way that, let us say this bit was put here, this bit was put here, and other zeros were put in between. Now, if you feed in this sequence to this encoder, so your ud is 1 plus d raised to power n minus 1, gd is 1 plus d. What will you get? You will get a output sequence which will have large number of ones, correct. So, what I did was, I just designed my interleaver in such a way that two adjacent ones were spread out, and as a result you noticed that I am getting a large number of ones coming out from this parity bit. Now, contrast it with the situation where, let us say, instead of shuffling this bit here, if I would have kept this bit, let us say here, and this would have been 0. So, this would have been 1 plus d cube, then what would I have got? I would have got 1 plus d cube by 1 plus d. So, this would be 1 plus d square. So, I would have only got 3 ones here, but now I am getting a large number of ones. So, I hope I am able to convey the role of interleaver. The design of interleaver is very, very crucial. You should design the interleaver in such a way such that the adjacent ones are separated out far apart, so that after interleaving, when the same information sequence is passing through the encoder, it generates a large parity sequence with large weight. Ideally, what you would like is, if the parity sequence coming out here has low weight, then this should generate large weight parity sequence, and if this guy is generating parity sequence with low weight, then this should generate a parity sequence with large weight. So, again I cannot emphasize enough the role of interleaver, because this is a very, very crucial component of turbo encoder, and it also helps in some sense randomizing the code, like make the code look random like, if you want to use that word. So, let us look at the structure of turbo code again. So, you note here I have two encoders. This is my encoder 1 and this is my encoder 2. Both of them are recursive or feedback encoders. You can see that each one of them has 8 states in this particular example. Now, the information sequence is coming here. It is a systematic code. So, the same information is coming out directly as one of the output, and then the input to the second encoder, this is interleaved. Now, interleaving is nothing but, as I said, reordering of the bits. The reordered bits are coming to the second encoder, which will then generate a set of parity bits. So, this is the structure of a parallel concatenated code. In this particular example, we are using convolutional encoders as constituent encoders. Now, in this graph, I have plotted bit error rate performance versus signal to noise ratio for a rate 1/3 turbo code and for block size more than 65,000. Now, note the typical performance. So, there is a region where there is a steep fall in bit error rate performance, and this region we call it waterfall region. So, this is called waterfall region. Just like a typical waterfall, that performance is coming like this. And then there is a region where there is hardly any improvement in bit error rate in spite of increasing the signal to noise ratio, and this is known as error floor region. Now, performance in the waterfall region is governed by the convergence behavior of the constituent encoders under iterative decoding algorithm, and we will discuss this in subsequent lectures. And performance in the error floor region is governed by the distance spectrum of the turbo codes. So, typically the constituent encoders, convolution constituent encoders that gives good performance are the ones which have short constraint length, typically 3, 4, like memory 3, memory 4, these are the ones that give good performance. If we use a more stronger code with memory 5, 6, then typically the performance in the waterfall region is not good. Now, what I have shown you is a parallel concatenation of two encoders. Now, these two encoders can be the same encoder, like what I have shown here. If you see here, both of encoder 1 and encoder 2 are same. Now, they could be same or they could be different. So, if the constituent encoders are same, we call it a symmetric turbo code, and if these constituent encoders are different, we call it asymmetric turbo code. I already mentioned this point, that choice of recursive and systematic encoders is very, very crucial, because for a recursive encoder, a wait 1 pattern cannot terminate the encoder, whereas for a feed forward encoder, a wait 1 pattern can terminate the encoder. That is why we should use a recursive encoder, and systematic encoders help in initial performance in waterfall region, and that is why they are preferred over non-systematic encoders, especially if you are interested in performance in the waterfall region. So, what we are doing here is, so this is information bit, right? This is the information bit that is coming out in the output, and then you have this encoder, which is generating this parity bit, right. Now, this interleaved bit is interleaved information sequence is coming here, and what this encoder 2 generates, this encoder 2 generates this parity bit. Please note that we are not sending the information bit corresponding to second encoder. Why? Because the information bits corresponding to second encoder is nothing but interleaved version of the information sequence that is being fed to encoder 1, and that is why we are not sending the information bits here. We are not sending the information bits of the second encoder, we are not sending it across to the channel. That is because from this information bit, if we just interleave, we can get back the information bits for the second encoder. So, you can see this is a rate 1/3 code, because there is one input and there are 3 output. This is one output, this is one output, and this is one output, right. Now, how do you get different rates code? So, this is a rate 1/3 code. Now, how do you get other rates? Let us say I want to design a rate 1/2 turbo code. How do I do that? So, I will do what I can do, let us say what is called puncturing. So, what do you do in puncturing? In puncturing, you remove some of the bits, do not send some of the bits. So, let us say at time t equal to 0, I transmit V1 and I transmit V2. So, I am transmitting 2 bits. I do not transmit V3. Then at time t equal to 1, I transmit V1 and V3. I do not transmit V2, and this I repeat. So, every odd time I transmit V1 and V2, and every even at t equal to 0, 2, 4 I transmit V1 and V2, and for other time I transmit V1 and V3. And at the receiver, what I will do is, so at let us say I receive this bit. Now, since I am not transmitting all the 3 bits, so what I will do is, for the bit which was not transmitted, I will assume that this bit is equally likely to be 0 or 1. So, I will put it as likelihood ratio of this bit being 1 or 0 to be same. So, that is what I will do. And similarly here, since I am getting received bit corresponding to only this and this, what I will assume here is, I will feed to a decoder that it is equally likely that this particular bit is 0 or 1, because I do not have any other information about this bit. So, this is known as puncturing. So, I am removing some of the bits, I am not sending some of the bits. So, if you are interested in getting higher rates, you can do puncturing to get higher rate codes. And that is what I mean when I said bits can be punctured from the parity sequence to produce higher code rates. We could also do puncturing of the information bits. So, I just showed you an example of puncturing of the parity bits. I could also decide not to send the information bits. Now, if some of the information bits are not sent, that means they are punctured, this particular code is known as partially systematic turbo code. And if I do not send any information bit, then of course, you already know this is a non-systematic code. Now, the encoder diagram that I showed you was using 2 encoders and 1 interleaver. Now, this structure can be extended for multiple encoders and multiple interleavers. So, I could have a situation, let us say I have encoder 1, I have encoder 2, I can have encoder 3. And what I can do is, I can have information sequence coming in, let us say U. So, this is directly going out, this is V0, this is V1, and then I have interleaver, which I am denoting by this pi. So, interleaved bits are coming to encoder 2, it is generating some parity bits V2. Then I have another set of interleaver, I am just denoting it by pi 2, and it is being fed to encoder 3, and I get another set of bits. So, the structure that I have shown you for 2 encoders and 1 interleaver can be extended for multiple encoders and multiple interleavers. So, this will result in a rate 1/4, what we call multiple turbo code. So, we use the term multiple turbo code. So, this is an extension of the conventional turbo code, which uses 2 encoders and 1 interleaver. Now, I have shown you that design of interleaver is very crucial, and there are multiple techniques you can use for designing interleaver. A very simple way is what is called block interleavers. So, the information that you want to interleave or you want to send to the second encoder, what you can do is you can store that data block wise, row wise. So, you fill that data row wise. So, once you come here, you then fill up. So, this is how you fill up the data. Okay. So, you are filling up the data row wise, but when reading out, you could read the data column wise. So, I can read data like this, and then I come here, read this data, come here. So, this is known as block interleaver. A very simple example, let us say my block size is 4. So, what I can do is I can put my data like this. First data I can put it here, second data I can put it here, third data I can put here, and the fourth data I put here. But while reading, instead of reading row wise, I can read it column wise. So, I first read 0, then I read second and read 1 and I read third, right. So, what did I do? So, this was my original data, but interleaved version is now what was there in. So, in location this, the same bit is there, but in this location now I am having what was earlier there in this location, and in this location I am having what was earlier I had in this location. So, interleaving is nothing but just reordering of data. You could also design it randomly. I will decide, okay, first bit I will put in this location, second bit I will put in this location. I just have to ensure that every bits are put in distinct location. No two bits are put in the same location, right. And ideally what you would like is, if there are like bit streams coming in which have consecutive ones, they should be spread out after interleaving. That is you would like to do. And there are class of interleavers like S random interleaver, which imposes some additional constraints which will allow that two adjacent bits are at least spread by some amount. Okay. So, that is interleaver. So, you have seen how we are constructing the encoder. It is a parallel concatenation of two encoders, right, and you have a interleaver. Now, how do we decode these codes? We are going to use an iterative algorithm. So, we are first going to decode one encoder, then we are going to decode second encoder, and these decoders will pass on information to among each other. So, after the first encoder decodes, it will pass on some information to second decoder saying, okay, I think these are the information bits. Now, the second encoder will take that input and process, and then it will give a new set of estimates to the first encoder saying, oh no, I think these are the values of information sequence, and this process happens in an iterative fashion. In fact, the name turbo codes come from the decoding structure. The turbo engine has this feedback mechanism, and the decoding structure of this turbo code is also the feedback. So, from one encoder to other encoder, and this is basically going around. So, from there this name turbo codes have come. So, we are going to use iterative decoding algorithm, and each of these component encoders are going to use this BCGR algorithm, and we already, when we talked about decoding of convolutional code, we already talked about how BCGR algorithm works. In the next lecture, we will talk about how the turbo decoding algorithm works. And this decoding, as I said, happens by block fashion. So, you wait until you receive n bits of data, because remember this interleaving operation, though it can be parallelized, typically done in blocks of data. So, you process, you decode the bits also in block by block fashion. So, the information can be arranged in blocks of data. Now, typically for better performance, as I mentioned, we typically try, initially the encoder is in all 0 state, and we like to bring back the encoder back to all 0 state after we have transmitted our information sequence. So, that is known as termination, and we terminate this turbo encoder by appending some tail bits to our information bits. Now, because of the interleaver, it is not always possible to have the same tail bits terminate both the encoders. You could design an interleaver which will allow you to terminate both the encoders, that is possible, but in general it is not possible to terminate both the encoders with same termination bits. So, you could either terminate first encoder, leave the second encoder unterminated, or you could send additional bits to terminate the second encoder. So far I have shown you that we are using recursive systematic convolutional encoder in a parallel configuration. We could also design same thing using block codes as well, and we are not going to discuss those in this lecture. Now, there are some disadvantages of turbo code, though their performance is extremely good. There are some inherent problems with turbo code. One is they have a large decoding delay. Typically, the performance is good for large block size. So, when you are dealing with large block sizes, then there is a lot of delay involved, because you are doing block by block post processing. And second thing is, typically if you are looking at very low bit error rate performance, there you just saw that because of error floor, their performance is not very good at very low bit error rate. Now, I will just conclude this lecture by giving you some references of some key early development in turbo codes, and you can read those references. So, this is where turbo codes were initially introduced by a paper by Baru et al. In ICC 1993. When this paper came, people did not actually believe the results, because they were very good performing codes, but subsequently multiple research groups were able to reproduce their results. Now, the next set of papers, these two papers by Benedetto et al. Unveiling turbo codes, some results on parallel concatenated coded and design of parallel concatenated convolutional codes. These were one of the first paper to explain why the performance of turbo codes is not very good at high signal to noise ratio, and why do they suffer from error floor. These were the first paper where they generalized by Divsalar at JPL lab, where they generalized it to multiple turbo codes, and this paper also gives some design rules of on how to design turbo codes. This is a nice by Hagenaar, this is a nice paper on iterative decoding of binary block and convolutional code. This explains the BCGR algorithm and turbo decoding BCGR algorithms in a very nice way. Now, in this lecture we talked about parallel concatenation. Now, this is a different variant where you could have a serial concatenation. So, you could have a encoder 1 here, then you could have an interleaver here, and then you could have another encoder. So, this variation was proposed by Benedetto and others, and this serial concatenation, though has little inferior performance in the water flow region, it has better performance in the error flow region. And finally, these three papers that you have discusses the behavior of the iterative decoding algorithm. Why choice of some encoders is good, how should you choose the encoders so that you have better performance in the waterfall region. This was nicely explained in these three papers, and each one of them used different technique. Ten Brink used mutual information, Divsalar used the evolution of the densities of the expressive information, and Al-Gamal used mean and variance of the expressive information, and they tracked it to get information about the convergence of the turbo code. So, with this I am going to conclude my discussion on turbo codes. Thank you.